Hey everybody, we're going to finish up chapter 7 today, and it finishes with an important lab procedure that I really wish we were able to do, but we can't because we're not in school. But I want to walk you through it, and I'm going to assign a video that I want you to watch where you're seeing somebody actually doing the procedure, because you will likely have to do this next year. And they will basically probably be under the assumption that you know how to do this. But again, recognize that a lot of other students in their first year courses taking first year chem will be in the same boat as you now, where they can't do the labs because they're at home because of COVID. So you're not going to be alone, but it will be a good idea if you've actually seen this. So before I move forward, I'm going to go ahead. I assigned some homework for yesterday, which were these 4 questions here on page 268. But I realized a couple of them are a little tricky, and I'm going to skip 3BC and 4B and C, and just leave you with 1, 2, 3A, and 4A. And I think I'm going to do 3A and 4A right now, just for practice. So I'm going to start with a clean board here. So for question 3A in the textbook, actually let me just pull the question up so you can see it. Whoops, cancel. Pull up the question so you can see it. Again, if you ever get stuck, notice that they've got really good solutions here in the textbook when they do sample problems. They walk you through step by step what they're doing, why they're doing it, how they're doing it. Okay, so I'm going to look at question number 3 here. Question number 3 is asking me what volume. So V is unknown of hydrochloric acid. So I know the strength of the concentration of the acid, right? It's 0.15 moles per liter, and I'm asked what volume it is. It says how much will be needed to neutralize this volume of this concentration of sodium hydroxide. So I've got a chemical reaction going on here between hydrochloric acid and sodium hydroxide. Okay, so let's go to my whiteboard there. And like I was saying, this is 3A, so I'm going to start with HCl, hydrochloric acid, and it's reacting with sodium hydroxide. Right, and we're told the concentration of the acid is 0.150 moles per liter, and that the concentration and that the volume of the acid is unknown. We're also told that we have sodium hydroxide there, and we have 25 milliliters. Let me do the concentration first. Not that it matters. Concentration is 0.135 moles per liter. And the volume is 25.0 milliliters. Now the reason why I did the volume second was because I have to convert this into liters, and I wanted to make sure I had room for this. So I know that 1 liter is the same as 1,000 milliliters. And my milliliters will cancel, and I'll be left with 0.0250 liters. So there's my volume of NaOH. Now, to find the missing volume over here, I'm going to be using all the way through this. I'm going to be using the same formula, which is C equals N over V. So there's a formula that we're going to be using all the way through here. If I rearrange this formula down here, take the V from down here up beside C and take the C down under the N, I end up with V is equal to N over C. Right, now to do that formula, I need to know N and I need to know C. I do know C, it was given in the question, but I don't know N here. Right, so before I can calculate the volume, which is what I'm looking for, I need to know how many moles of acid. Now, the reason why I skipped 3B and 3C is because the mole ratios weren't 1 to 1. But what I can see in this equation here, just let me pull this down a little bit, is that I have one H and one OH, so I'll get one H2O, and I've got one Na and one Cl, so I will get an NaCl. So if I was to write in my products here, I would get HOH, or H2O, and NaCl. And it's a 1 to 1 ratio. So the number of moles of NaOH that I have, will have to equal the number of moles of acid. And I'm going to try and do that with, I will do that on the test also. Okay, so my number of moles here will be equal to my number of moles here, because that's what neutralization is. It's when the number of moles of base is equal to the number of moles of acid. So, number of moles, again, if I look at the formula that I had down here, right, the number of moles, I'm going to bring the V down here beside C, so I get N equals C times V. Right, N equals C times V. And I know the concentration, it's given up the top here, which is 0.135 moles per liter, times my liters of 0.0250 liters, and I will get a number of moles which is, whoops, 3.38 times 10 to the minus 3 moles. Okay, so again, remember what we said a moment ago is that the purpose of a neutralization reaction is to have equal numbers of acid and base. So if I have 1.38 times 10 to the minus 3 moles of base, I have to have the same number of moles of acid. So now I can transfer that number over to the acid side, and I will get 3.38 times 10 to the power of negative 3 moles. Okay, so now I can calculate the V, the volume of acid, because I know N and I know C, given in the question. So I can calculate my V now. N over C, 3.38 times 10 to the power of negative 3 moles, divided by my concentration of 0.150 moles per liter. So I'm just going to take my number of moles here, divided by 0.15. I'm getting 0.0225 liters. So the question is asking how much acid I can neutralize with that base. I can neutralize 0.0225 liters of acid by using that amount of base. So whenever we do one of these questions, I will always be given enough information to either calculate N for the base or calculate N for the acid. And then as soon as I know N on one side, I can use it to do the math on the other side. Right, similar to what we were doing when we were doing the limiting reagent stuff way back in the course. At times like this, you're probably happy that we're not having to think about final exams. So we're gonna have to push hard to get through to the end of the course, but then when we're done, we're done. And it'll be kind of nice in a way that we don't have to think about doing that exam. All right, so there's question 3A. You know what? I think I'm going to change my mind and not do 4A, because it's the same as 3A. If you want more help, you can ask me tomorrow during our live class, right, in the morning. Okay, so I want to move on now to our last note for 7.5. It's a bit of a longer note because I'm trying to walk you through the procedure. So the procedure is called a titration, right? And in a titration, right, the purpose of a titration is to find the concentration of an acid or a base. Right, so the procedure, the purpose of this lab is to determine a concentration of an acid or a base solution. Okay, so that's the goal here. I'm going to give you a solution. You're going to see it in the flask, and when you look at it, you're going to say, okay, what's in there? I'm going to say there's an acid in there, and you're going to say, what's the concentration of acid in that beaker? And I'm going to say, you've got to find that out. So how am I going to do that? I'm going to do that using a titration. Or I'm going to give you a flask, and you're going to say, what's in the flask? I'll say it's a base in that flask, right? Sodium hydroxide. And then the next question will be, what's the concentration of the base? Because that partly determines the pH, which, and again, pH is an important piece for us. And I'll say, well, I'm not telling you the concentration of base. You have to do the titration to find the concentration of base. So that's the purpose of a titration, right? The purpose is to determine the concentration of an unknown acid or base. So in order to do this, well, how am I going to do this? I'm going to give you a second solution, which is the opposite. If you're finding the concentration of an acid, I will give you a solution of base to do the titration. Except when I give you this other solution, right, the opposite one, it has to be a known concentration, right? And once you know the known concentration, then we can basically do calculations similar to what we just did in that question a moment ago. Now, the one that's the known concentration is what we're going to call in this lab the titrant. It's what we're using to do the titration. Okay? And then ultimately, we're going to add titrant drop by drop until we've got an equal number of moles of acid and base. That's going to be called the equivalence point, when the number of moles of acid is equal to the number of moles of base. Now, because I can't really see exactly when the number of moles, because I'm not actually seeing molecules, I actually have to use an artificial way to try and decide when have I got the end of the titration. When do I have an equal number of moles of acid and base? Well, I'm going to use an acid-base indicator, right? And remember, the acid-base indicators are chemicals that have two possible colors, and they will change color when it switches from an acid to a base or a base to an acid. So that point in the titration is called the endpoint. You think, well, how is the endpoint different from the equivalence point? The equivalence point is actually when the number of moles is equal. The endpoint is telling me when I've actually gone past the equivalence point, when I've actually got more. I've added a little bit more, but it's pretty close. If I use that volume, I know that I'm going to be very, very close to the right amount. Right? So that's what the endpoint is. Now, remember, our endpoint here is going to be determined when I get that color change for my indicator. So part of the goal here, there are so many different acid-base indicators that we can choose. We've got to choose the right acid-base indicator. And again, we're not going to get into which indicator to use for which, because again, that's about a 2-day discussion. So we're just going to make sure that we're going to use what we're going to say is the best indicator to do the lab. Okay, and the best indicator is the one that changes color at around the pH where the equivalence point is, where the number of moles of acid is equal to the number of moles of base. And isn't that going to be pH 7 when the number of moles of acid is neutralized by base? Well, remember what my products are for a neutralization reaction. Right, the products are a salt and water. Right, products, when I put an acid and base and I get rid of them both, they neutralize each other. I will have this and this. Now it turns out the water's pH 7, we know that. But the salts, sometimes salts actually have a little bit of acidity or a little bit of basicity or alkalinity. So when I've added acid to base, if the salt is slightly acidic, then the pH won't be 7, it will be a slightly acidic pH. If the salt is slightly basic, then I'll end up with a slightly basic pH when I reach the equivalence point, when the amount of acid is equal to the amount of base. Right? So we really want to make sure that we have exactly the right indicator to make this work. Okay, so again, remember the goal here. To find out exactly what the concentration of my unknown solution is, I need to know exactly what the concentration and the volume of my titrant are. Now, when I'm making up a concentration of solution, I can calculate exactly how many grams, how many milligrams, maybe even how many micrograms I've put into the solution, so I can know the concentration of my titrant very, very well, right? This piece here is pretty easy. Okay, the purpose of today's lab is to figure out how much titrant do I need to add. Because once I know the amount of titrant in volume and I know the concentration, I can figure out how many moles of titrant there are. And then once I know how many moles of titrant, I know how many moles of the chemical that we're testing is called the analyte. How many moles of analyte there are. So there's two solutions here. One is the titrant. It's the one that I have a known concentration for. And the other one's called the analyte. And you're going to see that word coming up in a few moments. And that's the chemical, that's the unknown. That's the one that we're testing. Right? That's the one that we're trying to figure out what the concentration is. Now, the key to doing a good job with this lab, and it can be critically important, right? The key here is our accuracy. I want to know accurately what is the concentration of my titrant and how much titrant did I add, how much volume. Now, really what I'm going to do is I'm going to add my titrant drip at a time until I see whether there's a color change. Because as soon as the color changes, I know I've hit the end point, and I know the end point is very close to the equivalence point if I've chosen the right indicator. Okay, so I need to have the precise concentration, and I need to know the exact volume. So, like I was saying earlier, ultimately, I would love for you to be able to do this lab because it's a very important lab for chemists. A lot of chemists do it. If you work at a swimming pool for a summer job, part of your job might involve testing the pool water, and part of the analysis sometimes involves doing a titration right at the pool. Right? It's a way of testing the concentration of chemicals in the pool. Okay, so when we do this lab, okay, the purpose of this lab is to determine the unknown concentration of the analyte. Okay, the purpose of the lab is to determine the unknown or the concentration of the analyte. In this case, the analyte is hydrochloric acid. Right, so what is the concentration in moles per liter of hydrochloric acid? Now the question is, what kind of equipment am I going to need to do this lab? So first of all, I'm going to need to accurately measure the volume of my analyte. Right, I need to know exactly how much analyte I've got. So to do that, I'm going to use something called a pipette. Pipettes are kind of like a straw. Right? When you suck on the straw, it pulls the liquid up the straw. Except we're using nasty chemicals, so I don't want to be putting my lips on the pipette. So I'm going to use a bulb. I'm going to squeeze the bulb and then stick it on the end of the pipette and then let go. And as the bulb opens up, because it's rubber, as it opens back up into its regular bulbous shape, it creates a vacuum that pulls the liquid up the pipette. Okay, so here is the two kinds of pipettes that we would use in this type of lab. One's called a graduated pipette. That's the one on this side, and it's got graduations. It's got numbers all the way up. 2 milliliters, 4 milliliters, 6 milliliters, 7, 8, 9, 10 milliliters. So I can actually measure a volume using this thing. There's the rubber bulb that I would put on the end. And then again, remember, I would squeeze the bulb and then dip this into my liquid, put the bulb on top, and it's going to pull the liquid up. And as I'm watching it, at some point, when it gets higher than I want, then I usually pull the bulb off and put my finger on the top, and then slowly I let the liquid come back down to the volume that I want to use. Okay, and that works. That's one way to measure the volume. The other one is to use this one here. This is called a volumetric pipette. This one here is a 20 milliliter pipette. And for this one here, again, you can see that it's open at both ends. We can't see the top actually, but it should be open at both ends. And I'm going to do the same thing. I'm going to put the rubber stopper here on top, and when it starts pulling the liquid up, the liquid will start coming up. It will fill this big fat section here of the pipette, and this little line here tells me when I have exactly 20.00 milliliters of whatever liquid is that I'm measuring the volume of. So the reason why this is actually much more accurate than this, because of how skinny this is at the top. Right, it's got a big chamber up here for getting most of the volume, but then it gets really skinny up here, so I can very accurately determine how when I'm at the exact 20.00 milliliters. So this is called a volumetric pipette, and that's called a pipette bulb, and this is my graduated pipette. Okay, so I'm going to need either a graduated pipette or a volumetric pipette, and I'm going to need a bulb. Okay, and again, remember the bulb will draw the liquid up the pipette. Okay, second thing I'm going to need here is a couple of Erlenmeyer flasks. Erlenmeyer flasks are probably the most common one to use for this kind of lab because they're quite narrow at the top. If I swirl it a little bit, it's likely not to come splashing out. So these Erlenmeyer flasks are the one that we're going to use, and I'm going to put my analyte, the chemical that I'm testing, in this case it's hydrochloric acid. I'm going to put it in here using my pipette, right? I'm going to put it into there, right? And then my second Erlenmeyer flask would be one for collecting wastes, right? One that we usually have a waste container. You're actually going to have your own waste container when you do this lab. Okay, so you got two Erlenmeyer flasks, and you're going to transfer your acid into this Erlenmeyer flask. Okay, the next thing that we're going to need is the piece of equipment that measures the accurate volume of my titrant. So I've already added exactly 20.00 milliliters of hydrochloric acid, but the concentration is unknown. So to find the concentration, I need to know the number of moles and I need to know the volume. Well, I know the volume, right? I just measured it. The volume I just measured, it's 20 milliliters. The number of moles is going to be determined by the base that I'm going to add. So I need to calculate little n here, the number of moles for the base, and that will tell me how many moles of acid that I have when I've reached equivalence. So I'm going to use a burette. Okay, so the burette is this piece of equipment here. Okay, and it usually is glass. So you can see one on the right-hand side here, and it's graduated all the way up. It starts with 50 at the bottom, 50 milliliters, 49, 48, 47, all the way up to 3210 at the very top here. It's actually measured so accurately that because liquids expand when they change temperature or contract, this was actually calibrated at 20 degrees C. So if it's not really at room temperature, the accuracy is going to be a little bit off. So what we're going to do is I'm going to fill this long thing with my sodium hydroxide, which is my titrant. So the titrant goes in here. I'm actually going to put a funnel up top here. And I'm going to pour my titrant into the burette, right? And there's a little, this is called the stopcock. It's at the bottom. You can see it's in the picture here. In the picture here, you can see the stopcock. It's got a Teflon stopper in the middle with a hole in the center. And if this little the stopcock is turned so it's parallel to the burette, the liquid goes straight through it. But if I turn it so it's perpendicular, that's perpendicular to the pipette, so that it's 90 degrees to the pipette, then it's actually stopped and no liquid will get through. So usually it will be in the other direction, so it would actually be this way, and there's no liquid can get through, and then I will turn it a little bit until I see drops coming out, and then I will stop it again and see whether I've reached equivalence yet, whether I've reached equivalence or not, because the indicator will have turned color. So what I'm going to do is I'm going to open the stopcock and I'm going to let some of the base in. So what I've got in here is my analyte, which in this case is hydrochloric acid, and my indicator, which I think they're going to use phenolphthalein for the indicator for this lab. And phenolphthalein is colorless in an acid and a fuchsia pink in a base. So if I put a few drops of my indicator in now, because there's an acid in there, it'll be colorless. It'll have no color at all, because phenolphthalein is colorless in an acid, and I have an acid in there. Now I'm going to start adding drops of base. I'm going to start adding drops of base into here, and I'm going to swirl it. I'm going to basically just give it a bit of a... I'm going to leave it sitting on the counter, but I'm actually going to kind of move it in little circles just to kind of swirl it around, and I'm going to look and see, after I've added a drop or two or three or more, whether there's a color change. If the color changes, then I'm going to go back and I'm going to read, I'm going to read from the burette here how much volume did I start with up here. I don't always start at the top, and what volume was I at when the color changed. And the difference between these two volumes is the volume of titrant. In this case, sodium hydroxide volume. Okay, so that's the whole goal here, is to add my titrant to my analyte, right, until I get that color change. Okay, so there's the third thing I'm going to need. So I needed the pipette and bulb, I needed the Erlenmeyer flasks, and now I need the burette and the stand that's going to hold the burette. Okay, it's nice and sturdy. Now, other things I'm going to need a funnel to put on the top of the burette so that I can actually add the titrant to the burette. I'm going to need a washing bottle, a squirt bottle that's got pure distilled water in it. Soft safety goggles, absolutely, right, because we're working with acids and bases which can damage the eyes. We're going to be using an acid-base indicator. Like I said, we're going to use the one called phenolphthalein. Remember, the pH is silent, so pretend it's not there. Phenolphthalein, which is colorless in an acid and pink in a base. Right, and pink in a base. Right, so those are our two colors. So when I first put the phenolphthalein in, it will be colorless, and once I hit equivalence and go past the end point, it'll turn pink. So again, remember the analyte in this lab. The analyte is the acid, is the thing that we're testing, because the whole goal here is to find the concentration of the acid. I'm going to be figuring that out by using sodium hydroxide, which is my titrant, right? And it has a known exact concentration, right? And then we're going to go from there. Now, instead of getting you to watch the video, I'm going to ask you to watch that video on your own. And I think if I try to watch it now, I think it probably won't show very well. I think embedding a YouTube video within a YouTube video, if I remember correctly, it doesn't work too well. So I'm going to ask you to click on that link and watch that video. I think it's 6 minutes in total, and the fellow who's doing it explains exactly what he's doing, very similar to what I've just done. Now, so in this lab that he's doing, the same as the lab we're going to do, he's using sodium hydroxide for his titrant, for his base. Using sodium hydroxide, which is the base, for his titrant. That's the one that goes in the burette. And then I'm going to put my analyte into the Erlenmeyer flask with the acid-base indicator, the phenolphthalein. Right. And then I'm going to accurately look at the volume on the burette before I start the lab. And you think, well, why wouldn't you just always start at 0? because it can be really hard to get it exactly to 0. You might spend 15 minutes, you pour some in, and then you start bringing it down slowly, and you get down, oh, 0.14. I got too much. It's not at 0 now. I have to put some more back in and then try and get it to come back down. It's like trying to get exactly 1 second on your stopwatch, right? Really quite hard to do. So it doesn't need to be at 0.00. Right, we can start at any volume, so long as I know the starting and the final volume. If it starts at 1.5 and ends at 3.5, I know I've added 2.0 milliliters. So as long as I know my starting and final volumes, which is how the burette's going to work, and you're going to see in this lab, when you do the test lab that we're going to be doing, or the sample lab, that they're going to have a starting volume and a final volume, and to find the volume in the actual procedure, you have to subtract final minus initial. Okay, so to determine the volume of titrant added, we're going to once I know the volume of titrant that we've added, I can calculate the number of moles, right? And then I can use that to determine that will be equal to the number of moles of the analyte, which is the hydrochloric acid. And then once I know N, I can find the concentration of the acid, which is why we did the lab in the first place. Okay, so I'm going to walk you through a sample calculation here. So the sample calculation has, we're trying to find the concentration of sodium hydroxide this time. So this time, when we do the lab, I'm going to put my sodium hydroxide, which is my analyte, there it is in the Erlenmeyer flask, and C is unknown. And then I'm going to set up my Erlenmeyer flask here with the stopcock at the bottom, and this is going to contain my titrant, which titrant is, the titrant was hydrochloric acid at 0.5 moles per liter. Okay, so titrant in here is hydrochloric acid, HCl. The concentration is 0.500 moles per liter. And I'm going to find the volume used for the lab. So what I know is the concentration of acid right now, and I know the volume of NaOH that I put into the Erlenmeyer flask, and it says we're going to have a 25 milliliter sample of the analyte sodium hydroxide. So 25 milliliters is my volume for sodium hydroxide. .00 milliliters, which is 0.02500 liters. Okay, you can do the calculation. You've done this enough times now, I think. All right, and now I'm going to look at my formula and start the math. So I'm going to have a reaction between HCl and NaOH. Notice in this case that the NaOH, if I put phenolphthalein in here, it's going to turn pink right away. And as I add HCl, I'm going to keep adding HCl until the pink goes away. When the pink goes away, I know there's no base left because I have reacted it. And if I add any more acid, it will make the solution acidic because all the bases have been consumed, and now it will turn colorless. So either way, I can have either sodium hydroxide and HCl in either titrant or analyte, and it will work. So what I've got here, I know the concentration, 0.500 moles per liter. Now in one of the videos, they don't use the term moles per liter, they use the term molarity. So they use a big M, which means moles per liter. Right, that's the molarity, or moles per liter, or the concentration. The goal of the lab is to find the concentration of sodium hydroxide. we know the volume of sodium hydroxide. And if I look at the data from the lab, it says the starting volumes for the on the burette and the final volume on the burette were 2.46 milliliters and 34.58 milliliters. So I started at 2.46 and I finished here. So to find my volume of hydrochloric acid, it's going to be final volume minus initial volume. 34.58 minus, I haven't given myself much room here, 2.46, which is equal to 32.12 milliliters. Which is equal to 0.03212 liters. Okay, so now I'm done. Right now I've looked at the question, and now all I have to do left is the math. So to find C over here, which is what I'm looking for, C is equal to number of moles divided by volume, N over V. Again, remember that's on your periodic table. To find C, I've got V, but I don't know N yet, so I've got to find the N on this side. So the N on this side is equal to C times V. I know the C concentration is 0.5, and that the volume is 0.03212. So my number of moles is equal to 0.5 times 0.03212. I'm getting 0.01606. 0.01606 moles, MOLs. Okay. And I know that this number of moles here is the same number of moles that I'm going to need on the other side. So my number of moles here is also going to be equal to 0.01606 moles. And now I know N and V, I can solve for C, which is what the question was all about. All of this procedure, all of the work that was done here, ultimately to come with number of moles, 0.01606 moles divided by 0.02500 liters. Notice I got moles over liters, or moles per liter, and my C turns out to be 0.6424 moles per liter. Okay, or again, remember, we can replace moles per liter with big M, moles per liter. Okay, so that's how the calculation works. And before you go ahead and do the lab, I'm going to ask you to go and watch that video link, which is up here. Oh, darn it. Didn't mean to do that. And I want you to try these questions down here, which would be really good review before doing the lab. Okay, so tomorrow during class I'm going to talk about doing the lab, and I'll record it. So I will stop there. I know it's probably hasn't given you much time to do this, but if you get a chance to do one or two of these questions either tonight or tomorrow, I'm going to ask you to try and get a couple done. Let me see, page 273. Maybe if you could do question 7. Oops, undo. Question 7 from page 273. That would be good practice ahead of doing the lab. And then further down on the note, it says your turn. Okay, so you're actually going to read through the procedure. The lab is actually the one that's in the textbook that we normally do. It's on pages 274 to 5. The goal here is to find the concentration of an acid, which is acetic acid, which is the acid in vinegar. So the question is, how many moles of vinegar, of acetic acid, are there in a liter, moles per liter, of vinegar that you would buy from the grocery store? So I'm going to walk you through tomorrow during our class the steps that you would do from 1 to 16, and then I'm going to get you to watch this video here, and she's going to do the lab, and she's going to collect all the data for you, and you're going to record her results in this section down here, and then you're going to do the 4 analysis steps, and that will be kind of a virtual lab for us. Okay, so I'm going to stop there and leave that with you. I'm hoping to see many of you tomorrow for the live class. If not, definitely watch the recording. And just a reminder that there is the live class. There is a test on Thursday this week for Chapter 7. Wednesday will be a review day. I might make myself available for an hour on Wednesday morning if you have any questions, but I won't plan to do anything new or different. And I think that's it. Just a reminder, hopefully you saw my message in the announcements in the hub that if you want to get into the school, if you've got anything that you've left in the school, clothes, books, personal things, and you want to get them back, see the announcement in the hub about which day you can go in. You will only have 2 days that you can go